Let's look at some, like a very simplistic summary of these different exploratory data analysis techniques. This is by no means to give you detailed explanation. It's just for you to kind of remind you of the different things we do. So for example, we will visualize the data we have, right? Once we collect the data, we want to understand, and visualization is one of the best things for us human beings, because we are very good at seeing and seeing things and seeing different patterns. So that's why visualizing data is really, really important, both in terms of understanding the data for us, and later on in the presentation phase, presenting to others, it plays a very important role. So we can do univariate analysis by looking at each of the variables separately. We can do, right, so there's two different wine classes here, and then we can compare them, how they look like. Time series analysis is another thing. Is the pattern here is really important, because when we look at the table of values, we cannot really see this pattern, but here, for example, we can see the percent change in driven kilometers or by miles, or miles in different cities, and you can see the clear impact of the COVID, how it drastically decreased through that period and then slowly increased after that. You can see some of the cities recovered better, some of them were less, and this behavior is quite nice to see, nice to look at, by creating a simple time series plot like this. Another similar thing, but for countries this time. So you can see the different behavior, and you can see also the behavior during the pandemic and slightly after the pandemic. I mean, it was still the pandemic period, but at least you can see kind of the pattern where blue is, in this case France has much less traffic, but then after the period it has the most traffic there. So that's quite interesting to see that this behavior during different periods of time. Bivariate analysis is where we include two different variables, like in this case this is x1 and this is x2, so that's why it's called bivariate. And then we want to see their relation, right? The relation between the two variables. This is especially good when you have two numeric values, so that we can see whether there's some kind of correlation between them. If it is increasing like this, there's strong positive correlation. Decreasing like this, when one is increasing, the other one is decreasing, right? So this is a strong negative correlation. This is a kind of moderate behavior, still pretty strong. If you were to ask me, when it's kind of randomly split all around, this is basically no correlation there. And then once you plot the data, you might also see some non-linear relationship between the variables, right? It doesn't always mean that there should be some kind of linear relationship. It can be totally non-linear, as in this case. So you see kind of this behavior, or if you were to divide this into two areas, this is a negative relationship, while there is positive relationship after that period. So this is another way to look at the data. That's why visualizing data is very important, because for this example, if you were to calculate the correlation, it will come with a very small value, because it's kind of random. But then when you plot it, you see actually it's not a small correlation. There is some relationship here. But again, be aware that correlation is generally good when you want to see the linear relationship, the linear association between the data points, between the variables. It's not good to assess the non-linear association between the variables. Okay, so keep that in mind. That's important. Of course, when you have many variables like this, it can be hard to create one by one bivariate plots. You can also create like a heat map like this and see what kind of variables are highly correlated with each other. Pairwise plots is another way to look at the different relation between the binary variables. So you can create scatter plots, you can create density plots. You can also put regression lines onto them if that's a valid scenario, and see how the variables relate to each other. Missing data is important to deal with. You cannot use missing data in many models, so you have to either clean them, impute them, or get rid of them. So by visualizing it, you can it can help you in your decision making. If you have variables like this where almost everything is missing, you can maybe drop them, because they basically don't provide any value. If you have some variables where there's some missing values, you can try to impute them accordingly. Dealing with missing data is always hard. at the end, it's a guessing you do, so there's no real correct way, I would say. But in my opinion, making use of the domain knowledge is the best approach here. What do I mean by that? It's basically not just, relying on, okay, I will just input with a mean value, or I will input with a median, or some rudimentary techniques like that, but rather, what do you know about the data? How can you make use of it? Okay, so if you have flight data, right, let's say there is origin and then there's destination, right? So there might be some company that flies between New York to O'Hare, and let's keep it very simple, New York to Los Angeles, LAX. Okay, let's say this is the only two destinations it flies. It always goes from New York to O'Hare or New York to Los Angeles. Now let's say for this company you have some missing rows, right? So let's call this company XYZ. So this company XYZ, in your data, you have some rows for it, XYZ, right? So let's say this is origin, this is destination. Okay. So and you have more information like flight time and different things like that. But let's keep it simple. Let's just look at origin, destination now. So, well, okay, actually I need to include flight time as well. So flight time, let's say New York to O'Hare, I don't know, 2 hours and 15 minutes here. 2 hours. Okay, my writing is getting very bad. 15 minutes, and I don't know, New York to LAX is about 6 hours. So 6 hours and 30 minutes in one flight, and you have some other flights as well. But you kind of see a general pattern that it's about plus minus 2 hours for Chicago and about 6 hours to New York, from New York to LAX. So I think this information is much more useful than just some other general technique. How can we make use of it? So let's say we know the flight time of this flight is 2 hours and 20 minutes, and this one is 2 hours and 35 minutes, and last flight is 6 hours and 45 minutes. All right, so you have that information. What you don't have is sometimes you are missing the origin and sometimes you're missing the destination. Okay, so your data, let's say, looks like this. Okay, now one of the techniques for categorical variables like this is like, okay, look at the most common value and then fill it in with that. So let's say your most common value is I don't know, probably it can be, I think New York probably is one of the most common destinations, right? But then if you just fill it in with New York, you're kind of saying New York to New York. That's not possible, and it's 2 hours. New York to New York is 6 hours. So you're already wrong there. So that's not good. Let's say you put a condition on this. So, you say, okay, I will fill it in with the most common value, but if it is the same as the origin, I will go with the next common one. The most common one, next one is San Francisco. I don't know I'm not sure about San Francisco. I think it was SFO. I'm not sure. Let's say it's SFO. So let's say you fill it in with SFO, right? Let's change the color here so that we don't mix up everything. Let's go with this blue color. So you say, okay, this is SFO and this is SFO. And you do the same thing for origin as well. The most common origin is, let's say, New York, and you fill that in. Okay, your luck worked well for this origin because it's really New York for this company. But then for this one, this company doesn't even fly to San Francisco, right? Still, because it's just the most, common one, or the most second common one in your data, you filled it in with SFO. You might be happy with what you did because it was a very simple technique. You spent 5 minutes on it and you just moved on thinking that you're doing something good. You actually messed up the whole data, right? You just created noise here instead of doing good. I think it would have been much better if you just dropped these rows rather than filling it with totally wrong information in this case, right? So what you didn't do is you didn't make use of the domain knowledge, the domain information. One thing we know about this company is that it never flies outside of or O'Hare and LAX. So this SFO is wrong. So you already have some information here, and based on the flight time, the flight duration, you can estimate, okay, if you were to create a small table, saying that for O'Hare flights it takes about 2 hours, and for LAX flight it takes about 6 hours, you would have said, okay, if this is the case, I will, based on the flight time, based on my table, this is ORD, and this should be LAX. You're making use both of the company name, the origin. You're also making use of that, so that's another confirmation that it's coming from New York, and based on the flight time, you're filling this information in because you know something about this company, something about the duration. And for the New York as well, so you could make, okay, the destination is O'Hare, company's XYZ, flight duration is 2 hours, so this must be, well, you already know this company always flies out from New York, but just kind of working here with the data, so you'll say, okay, this is New York. And of course the company will fly back from New York, so it's not only out from New York, but it's New York to LAX and New York to O'Hare, back and forth. So you get the idea, right? So it's a simple example, but again, this is a very valid scenario for many cases. So how much can you make use of this domain knowledge? If this is possible, make use of that. And after that, maybe go into, okay, should I use the mean? Should I use the median? But again, I wouldn't say any of those techniques are correct at all. At the end, they are very simple techniques. It's just to help you fill in the data in one way. So as I said, dropping the columns, if there's many missing values, is good. If there are rows where there is, almost everything is missing on that row, that can also happen sometimes. Like that measurement is, that person or that entity or that observation basically is not good. There's lots of missing values, maybe you should drop those as well, right? So that's another thing. All right. Good, let's continue. So feature engineering is something that you should generally try to do in your data analysis and data preparation for your machine learning models, because when you engineer new features, it might be very helpful rather than using the raw features collected. This is especially valid if there's some kind of measurements from like devices, like for example, I don't know, like sensors and things like that. But even in other scenarios, it might still be helpful to create new features. Of course, just creating new features doesn't always mean it's always a good thing, because if you create just too many features, you might end up with redundant ones, meaning they are very similar to each other, but you just create more and more. So that actually is also not helpful for machine learning. Just because you have more, it doesn't mean it's good. So you should also include feature selection into your process. So you can create some, but you should also select some and get rid of some features. So these are some ideas basically that you can apply. For example, for image, right? If you are getting an image, we are trying to extract some features out of it. So, but for many other data sets as well can be a valid scenario. So for example, in audio, they try to get the decibels and I don't know, the frequency out of that data and try to use that and things like that. Yeah, as I said, if just creating too much features is not a good idea. Just be careful on that. And if you add too many correlated predictors, it will decrease the model performance. So just, that's, you should be careful on that. So we talked about handling missing data a bit. So this is kind of some common methods out there. So like for, using the mean median values for continuous values, imputation with just constant value, imputing from distributions, imputing using models. So this is the more complex one. So here basically you're making use of other models to estimate the missing value. So it's kind of like a pseudo classification or regression model you use before you do the real machine learning model. Here you basically use those to estimate those missing values, and then you have a full data set and then use that to train your final model, basically, kind of an idea. You can delete the columns, as I said, or delete the rows. And this depends on many things, but one of them is data availability. If you have lots and lots of rows, so if you just delete, I don't know, 5% or maybe less number of rows, that probably is okay. It won't affect your model too much. But here, of course, you have lots of data, so you're good with it. If you have very few data, then you might try to do some imputation, which might be more helpful for your data. Normalization and scaling, standardization, right? Where we take the mean and sigma value, the standard deviation, and standardize the variable, or normalize the variable by using the min-max scaling, is helpful in many models, especially the models where, you know, some kind of distance is used, or basically the scale will play a role in terms of affecting the coefficient of the values, like regression models, clustering, principal component models, principal component analyses, the k-means, k-nearest neighbors, support vector machines, neural networks, image processing. All these will require that the variables in the different columns are very similar in terms of the scale, in terms of the range they have, right? The scale invariant models, these are generally the decision tree based models. Decision trees, the random forest, gradient boosting, kind of the models which are decision tree based, they will not be affected by the different scales in your data, because each time the model will select one of the features only. So that's why the interaction between the different variables is not affecting the model. That's why you don't need to apply standardization on these. Again, of course, if you do it, it shouldn't, it might affect the model still, so I won't really say anything on that. So one of the things to check whether it improves the, you know, models or not is to do validation. So you do it before, train the model on normal data, look at the validation score, apply standardization, train the model, validate the model, and then see the performance, compare them, and see whether standardization or normalizing does have any impact or not. That's one way to do this. If you have categorical data, we said you have to combine, you have to convert them into numeric types. All right. So some of the methods are listed here. So one-hot encoding is one of the most common ones, but there's a few other methods as well. So that's one way to do this. So one-hot encoding is basically each of the unique values in that variable will have its own new column. And then for that row where that value is present, it will take a value of 1. For any other rows, it will be 0. For any other values, any other values where they are not present in that row will be 0. So for example, human, penguin, octopus, alien, they will have their own columns, as you can see. And for the first row, human is present, so that human value will be 1, everything else will be 0. Second, human, again, 1, 0, 0, 0. Penguin, in this case, for row number 3, penguin will be 1. As you can see, penguin is 1. Everything else will be 0, and so on. So this is called one-hot encoding. Dimensionality reduction. So we talked about creating new features and feature selection, right? Dimensionality reduction is you're trying to reduce the number of dimensions, but here you're not selecting features. Here what you do is you take the features, you combine them. For example, principal components is a linear combination method. So you create new features basically out of your old features. Okay, that's what it means. So you take them in a way, you kind of combine them and then create new features. But then what you do is here in the next phase, you can select just a few of those new features, right? So now you will have less number of dimensions. In principal component, right, it tries to preserve the most variance in your data. So that's why, for example, if this is your data, this is the principal component 1, because this is the largest variance happening in this direction, and the second one is in this direction. So this is the second component, right? So you will have, at the beginning, you have 2 variables, x1 and x2, right? And this is how the data is scattered around. So this is your principal component 1. As you can see, it's a combination of x1 and x2. So let's call this P1 and this is P2. P2 is also a combination of x1 and x2, right? So you will have 2 new dimensions, new features here, P1 and P2. P1 has the largest variance, P2 has the second largest variance, and they are perpendicular to each other. So this is kind of the main idea behind principal component analysis. What you try to do here is you will choose just a few components, the first few components. So that's why if you had 100 dimensions, so here the example is for only 2, but if you had 100 dimensions, let's say after this, maybe by choosing P1 up until P10, you kind of get the same performance as your model did with 100 features. No, so now using this is much more efficient because you have less number of dimensions. So in machine learning, less, if you can achieve about the same performance, less is always better. Less can be in terms of the dataset size. It can be in terms of the dataset size, number of rows basically. It can be in terms of the variable, number of variables, right? From 100 to 10. So if you are achieving about the same performance, choosing this is better, is beneficial. And also in terms of choosing simpler models. So if you have here, if you're doing this with neural networks, which is quite a complicated model, and if you can achieve the same thing with logistic regression, if you're achieving the same performance or quite close performance with logistic regression, then logistic regression is better because it's a much simpler model. So less is better in general. So principal component analysis basically tries to do this. It tries to reduce the number of dimensions by combining them in a linear way. And the new components, the first few components will, we hope that it will achieve the same performance. So in terms of choosing the components, generally the idea is, okay, we will choose the first n components that in a combined way will explain, let's say, 90% of the variance in the data or 80% of the variance in the data, right? So once those number of components are selected, you can train your model, test it, and then see the performance with the previous model, which was tested on the full data set, and then see how they perform. So that's another way to choose the number of dimensions there. Linear discriminant analysis is another way to basically choose the number of components. It's also a way to reduce dimensions. This has labels though, so this is supervised learning. This is supervised learning, the linear discriminant analysis. In principal component, it's a unsupervised learning because it doesn't make use of the labels, okay? Just a small but important distinction there. All right, so that's it, guys. Thank you and have a good day.